Okay, so thank you for being back. And our next speaker is Boris Pioline. So he's telling us about counting Calabi-Yau black holes with modular forms.
Thank you very much. Thanks to all the organizers, not all of them being Italian. It's a great pleasure to take part in this workshop of the SEED seminar. In fact, it gives me an opportunity to discover this beautiful institute, and also I'm all for any kind of activities between math and physics. So I'm glad to be able to participate in that. I wish I could have followed more of the activities during the last year, and hopefully I will do more in the future. So I understand that the background here is quite diverse, both physicists and mathematicians, and many of you probably have not that much knowledge either of string theory or algebraic geometry or modular forms. So I'll try to keep the discussion as broad as possible, not going into too much detail. However, the goal is really mathematical and is to compute integer numbers, so it's hard to spare the details. So, but I hope you'll be able to catch some interesting concepts along the way. So the motivation comes from physics, as I said. It's a long-standing problem, which is to try to understand the microscopic origin of the entropy of black holes in general relativity. Can be argued just from the macroscopic properties of Einstein's equation that we should associate to every black hole with the horizon area A, an entropy, which is the area over 4 in the natural scale unit, Planck scale unit. And the big question for a long time has been, can you understand this entropy as the log of some number of microstates with the given macroscopic quantum numbers, such as the mass and the momentum and so on? And famously, string theory provides a positive answer at the quantitative level in a very restrictive setup, which is the case of so-called BPS black holes, that are black holes that preserve some amount of supersymmetry in vacua, in string constructions, which themselves have extended supersymmetry. And it was a key insight already 30 years ago by Strominger and Vafa, building on some much larger body of work, that you could understand this black hole microstate as being some kind of solitons in string theory. They are called D-branes. They are extended objects which can wrap on the internal manifold. I'm sure all you know that string theory likes to live in 10 dimensions, we like to live in 4. So there are these D-branes that can wrap inside this international 6-dimensional manifold. And so the problem becomes to try and count the number of such microstates. So back 30 years ago, these people showed that indeed you get the correct exponential growth, including the numerical coefficient 1/4. But we like to go beyond just the growth to actually compute well, first subleading corrections, which would tell us about quantum effects, but also at the end of the day, have an actual counting problem. And I should say that that counting problem will be quite different from the one by Nicolas in the previous talk. It is not just combinatorics, it involves the details of the algebraic geometry of the internal space, but we'll use some kind of similar methods. This will be generating series. They won't be algebraic. In fact, they will have essential singularities, and that is the reason why there is this exponentially large growth in the number of states. But so you might say, why should we try to compute integer numbers in physics, computational physics? Well, really, the motivation comes from mathematics, because there is a very precise definition of the numbers that we're trying to compute. This counting of BPS black hole macrostates in the framework of algebraic geometry. I'm not an algebraic geometer. I've been writing papers over the years. I have some idea of what it means, but so to be able to use the concepts. But obviously, this is a very complicated problem in algebraic geometry, but the insight from physics can give very useful conjectures that you can then try to prove. So the correct formalism to describe these D-branes wrapped inside the internal space is the notion of derived category of covariant sheaves. That's a mouthful, but covariant sheaf is some generalization of a polymorphic vector bundle where the rank of the model can jump at some higher codimensional size. So if you have a bundle which is supported on the whole internal space, which would be a Calabi-Yau manifold, it's an algebraic variety with very specific properties, but which is kind of the staple of any string theory construction in 4 dimensions. So if the rank is constant, basically you have some brane that wraps the whole Calabi-Yau, the number of branes given by the rank of the vector bundle. And in physics, we call that a D6 brane because it has 6 dimensions that wrap the whole Calabi-Yau. But if the rank is only localized on some codimension 1 loci, some divisor, then it's a D4 brane. Could be localized on the curve, it's a D2 brane. It could be localized at a point inside the Calabi-Yau, that's a D0 brane. And so that the current sheaf is such kind of object. It carries a so-called chain character, like any vector bundle. So chain 0 is the rank, first chain class, second chain class, third chain class. This corresponds to these D6, D4, D2, D0 charges. Now, Giraffe category means something much more complicated than the vector bundle. It means a complex of vector bundles. And it's actually important to, if you want to probe regions in the modularized space where the Calabi-Yau is not just very large, but can have a string size. It's also a very robust mathematical concept. So the problem now just becomes a purely mathematical one in Donalson-Thomas theory. That is to compute. So you fix the chain character. So that's in physics that would be the vector of electromagnetic charges. John, there are both electric and magnetic, and many of them, not just like in the standard model or in Maxwell theory. So you want to count how many objects or stable objects in this category exist for given value of that charge gamma. But you don't have to specify the mass because these objects being preserving supersymmetry, the mass is determined by gamma. But what you do have to specify is the actual shape of the internal space, so the moduli of this Calabi-Yau. Calabi-Yau manifolds have a high dimensional space of parameters, which includes both complex structure deformations and Kähler structure deformations, and those parameters are actually the Kähler moduli. And then the question you want to ask is, how does it grow as you scale up the charge, which would be scaling up the mass? And in mathematics, it's a well-defined problem, but very hard to control. So we want to see what string theory tells us about it. So it's important that this counting problem depends on the moduli of the internal space. Of course, you're counting integers, so it will only jump by integers, but on some discrete loci, generally some real codimension 1 loci. But in general, it will be chamber dependent. And well, if the internal space is very simple, like a 6 torus, or a Calabi-Yau twofold, which is called the K3 surface times a 2 torus, then these jumping problems are actually quite mild. Like it doesn't occur at all for T6. And in the very specific sense here. And so these kind of internal spaces have been studied to great extent in the past literature. Basically, there is a complete story about counting D branes on T6 and counting on K3 plus T2. Has some interesting relations to number theory. But the real challenge is to do this for a general compact Calabi-Yau threefold.
Is there a way to see why this gamma equal to infinite approach infinite limit is stable?
No, so for any such gamma, you have to compute the stable objects in this category. So in general, this category describes multi-particle states, and you're looking for the bound state spectrum. And yeah, that's the main source of the difficulties. So if this Calabi-Yau threefold was actually non-compact and so-called toric, then this problem reduces to a combinatorial problem of the somewhat related to the previous talk. It would be like counting plane partitions in 3 dimensions and some kind of gluing of such things. But here we're trying to aim for a general compact Calabi-Yau threefold. The simplest example that people like to discuss is the quintic in P4. So take the degree 5 polynomial in projective space of 4 dimensions. That gives you a 3-dimensional space, which is Calabi-Yau, which has been kind of main example throughout to discover many phenomena that are very related to neurosymmetry and so on. But we'd like to be as general as possible. Okay, so as I said, it's if you want to do this counting, it's useful to construct generating series. And in fact, there are I'll review some arguments why suitable generating series of such so Donalson-Thomas invariants, which are counting specific set of black holes which do not carry any D6 brane charge. So they are supported on some kind of divisor inside your Calabi-Yau. But the divisor class is fixed and you allow the D0 brane class to be, so the number of points to be arbitrary. Then there are reasons to expect, at least physically, that these generating series will be modular functions. They will have modular properties. And as a result, their asymptotic growth is very well controlled and allows to make contact with the Becker-Chan-Hawking entropy. So I think everyone in this room probably knows what is a modular form. If not, it's just some generating series, some Q, some Cn Q to the n minus delta. In general, the powers of Q could be shifted by some in general rational number. So this number Cn is the one you want to compute, but the property is that this function, as a function of tau, where tau is the log of Q over 2 pi I, then this is invariant under fractional linear transformations in SL2Z up to some prefactor, which is called the weight. And that's a very powerful statement. Geometrically, it gives rise to very intricate analytic structure. But if you're interested in determining the growth of these Fourier coefficients, well, in fact, it's entirely determined by this shift. So basically the leading negative power of Q in this series. So this is sometimes called Cardi formula. It really goes back to Ramanujan and Hardy. And it's very robust. It assumes, well, basically transformation on the tau goes to -1 over tau, which is one of the generators. But you can tamper around against this transformation rule. So in fact, this tampering occurs when you look at general Calabi-Yau threefold, like the quintic, as I'll explain, and as we've been discovering in the line of research with Sergey Alexandrov, Jan Manshot, and a number of other authors, references will come later, is that in fact this generating series, due to this wall crossing phenomena, they are not just, are not Mach, strictly speaking, they are so-called Mach modular. This is something that maybe you are less familiar with. It's a tampering of this transformation rule, which might look very ad hoc and strange. So it means that it says that this function, generating series, is not just modular, but it picks out a non-homogeneous term in its transformation. Of course, you cannot put any non-homogeneous term here. You have to make sure that this is consistent with the group law. And one such class of terms is given by something which is called the non-holomorphic Eichler integral of some other modular form G. So G is sometimes called the shadow of the original F. It's an ordinary, in the simplest case, it's an ordinary modular form of weight 2 minus W if F at weight W. And so you see this is only a function of tau here. Tau occurs in this integrand. But it depends on the actual choice of transformation. And you can check that it satisfies the co-cycle, the group law. So there's an equivalent way of saying the same, which is to say that your original function f was not modular, but there is a way to repair this modular anomaly by adding a non-holomorphic term, depends on tau bar here. This term involves a similar type of integral, but now you integrate from minus tau bar. So if tau was in the upper half plane, minus tau bar is also in the upper half plane. It's like the reflection with respect to the vertical axis. So integrate from minus tau bar to I infinity of this function, the shadow. And the claim, well, this is designed exactly such as to cancel this anomaly. But it's at the cost of having non-holomorphicity. And in fact, you don't know a priori what the shadow is if you're just given the Q series. But if you know the holomorphic non-holomorphic completion, then you can read off the shadow by taking just the top bar derivative of this gives the f of tau. The top bar derivative just acts on the lower bound of this integral, and you just recover this ordinary modular form. So such a structure as, yes, please.
So I was just wondering, this you mentioned on the previous slide that there's some physical arguments that you expect that there should be some modular properties. I mean, is it already clear from these arguments that you would be expecting something modular, or is it?
Yeah. So in fact, the arguments make a very sharp prediction for what is the modular anomaly. So what is this non-homogeneous term in a transformation? I mean, the problem is that those are physical arguments. They are very precise and robust. If you ask a mathematician why that should be the case, okay, currently there's very little known. I mean, if I have time, I'll make a couple of examples where there is some understanding of it from algebraic geometry. But actually, this expectation was first suggested by physics, and then it's a task to establish it mathematically. But the physics prediction is very sharp and very precise, and so you can test it. That's what this talk is about. But I just wanted to mention that this type of structure, it looks very ad hoc, but in fact it appeared before. In fact, the first time it appeared in hindsight was in the physics of trying to understand superconformal field theories. People in the 80s, like Eguchi and Tomina and so on, were trying to understand characters of superconformal algebras, and they came across a structure, but it actually goes back much earlier to Ramanujan's lost notebook, and it was only understood. So Ramanujan listed some Q series, which he claimed had nice modular properties, or something of that spirit. And it's only at the beginning of the 2000s, in the PhD thesis of Zwegers, that it was understood that the actual modular property is realized in this way. But in fact, what I'm going to what happens in string theory on general Calabi-Yau is in fact more general than that. It's not just that there is a holomorphic shadow that controls the transformation. The shadow itself is a mock modular form, so there's kind of higher depth version of that problem, which was not really thought about first in mathematics, but is quite generic, and is expected to show up in many other type of examples. So maybe that's something you can use if you're not interested in string theory or algebraic geometry later. Okay, so this was pretty much the introduction. So the talk is to try to test this modularity conjecture, so to compute actual numbers in this training series, and try to see if they fit the expectation from modularity or mock modularity. And that's a complicated problem, but it turns out that mathematicians have developed tools to do this. And in fact, this work I'm going to talk about is based on some collaboration with Soheyla Feyzbakhsh. She's a mathematician in the Imperial College. And together with Richard Thomas, they have developed some set of relations between various types of enumerative invariants of Calabi-Yau manifolds, especially the Donalson-Thomas invariants that we're interested in, but also the counting of curves, which I'm going to review now, which is a much older story. And using these relations, we can actually perform these computations to a large number of coefficients and get some very striking checks of these properties.
Excuse me.
Yes, please.
Let me ask a little, it's a little ignorant maybe question. So if one wants to count points in Calabi-Yau manifolds, then there is an analog of modular forms, which are maybe paramodular forms. They have more moduli.
I'm not sure what you mean by counting points. If you're just interested in counting
points in Calabi-Yaus over finite fields.
Calabi-Yau over Q. Okay, so
it's a different counting.
It's a different counting problem.
Yeah, so there paramodular forms appear. So in your language, do these paramodular forms have shadows or non-holomorphic versions?
Well, that's a complicated question, but let me emphasize that the modularity that I'm talking about here is indeed not the same as what people may have heard about modularity of algebraic varieties, which is related to counting of points over finite fields, subject to the Lean-Veil conjecture/theorem. Indeed, that produces some modular forms, or maybe paramodular, depending on the Picard number of the Calabi-Yau and so on. And currently, those are two different stories. There's no indication of any connection.
There's no indication.
So here we're not counting points over finite fields. We want to count these stable objects. So, in particular, if you ask what would be the invariant counting points in the Calabi-Yau threefold in this case, in the sense that I understand, well, the points can just probe the whole Calabi-Yau. So the invariant that counts it is just the order number of the Calabi-Yau. It's very boring. But once you start counting the sheaves, which are supported on divisors, then it becomes a very rich and interesting story.
So counting of sheaves, which are integer numbers, cannot be done using Veil conjectures.
No, in fact, you are perfectly right. You can also try to use these Veil conjectures to actually count these stable objects. These objects have their moduli space on their own, and basically you want to compute the order number of that moduli space. So you could try to go over finite fields and do that counting. And in fact, that has been done in the local Calabi-Yau, so historic examples like local P2. You might know that these invariants are related to the Vafa-Witten invariants. And in that case, in fact, years ago, Yoshioka and others used counting over finite fields to determine this order number of moduli spaces. But it's different than counting points of the Calabi-Yau itself.
Thank you.
All right, thank you. Yeah, so please do continue to interrupt me with questions. I have 39 slides. I'm not planning to go through all of them. Some of them are very technical. I'll probably skip them. Okay, so let me continue. So that's the plan. Okay, but I'll first start by some background review on what kind of enumerative invariants are available and also interesting for physics, because these computations will rely on a set of relations between them. So the oldest kind of invariants are the so-called Gromov-Witten invariants. It's counting maps from, in general, a genus G Riemann surface into the Calabi-Yau, such that the image of the map has some fixed class beta. So it's a number which I denote by Gromov-Witten beta G. And well, it's very robust in the sense that it depends only on the symplectic structure, not on the complex structure. But it's not an integer in general. It's a rational number because this space of maps has kind of orbifold singularities and so on. And it's a very interesting story, but it leads to rational numbers. And well, the physics of it is that it determines certain higher derivative couplings in the low energy effective action. As you look at your effective supergravity in 4 dimensions, it has the Einstein-Hilbert term, and it has some gauge couplings, and then it has some higher family of higher derivative couplings. I'm not displaying them, but basically they are determined by this generating series where you fix the genus G and you sum of the all classes beta, all curve classes beta, and using some chemical potential or fugacity, sometimes people call it T, which is conjugate to beta. So this T you can interpret it as the Keller modulus of the Calabi. And well, it's famously computable using ideas from string theory, namely mirror symmetry. It was first discovered in the context of the quintic by Candelas and friends in the early 90s, but it holds in complete generality. If at least for the first two, so if the genus is 0, counting rational curves, or genus is 1, counting elliptic curves, embedded elliptic curves, then you can use mirror symmetry to that accounting, reduce it to some period calculus. And then, well, to go to higher genus, well, in principle, you could try to enumerate these curves. It's very complicated in general, but you can use there's a set of so-called holomorphic anomaly equations which relate all these FGs of increasing G. But even though they are holomorphic, there is, in fact, they themselves have their own non-holomorphic completion, which is very constrained by these equations. And it's a technology which has been first set up by Bershadsky and friends in '93, and then implemented in fairly efficient way by Rank, Klemm, and Albrecht, Klemm, and many collaborators over the years. And in principle, it determines the whole set, but at any time you do this, you integrate this holomorphic anomaly equation, you have to supply some kind of constraints, some boundary data, which fixes the holomorphic anomaly. And it turns out that there's only a finite number of such constraints that you know. They have to do with, well, maybe I should not go into too much detail, but yeah, in fact, it will come a bit later. And currently, there is a maximal bound, which for the quintic would be 53, where you just run out of constraints. And unless you have an alternative way of computing this, you would just start. And part of what I'm going to explain is a way to overcome a little bit that constraint. Now, I said that these Gromov-Witten invariants were not rational, but in fact, they were not integers, but there is a way to extract integers out of them, which was first understood by Gopakumar-Vafa in '98, which is to consider this learning series of Gromov-Witten invariants. Now you let also the genus be arbitrary, as well as the curve class. But you re-expand this series in a kind of funny way. Instead of expanding in powers of lambda, which is conjugate to the genus, you expand in powers of sine lambda. And in fact, there is also some slight refinement of this procedure. And so the statement, which is now a mathematical theorem due to Yonel and Parker, is that the coefficients which appear in that re-expansion are actually integers. And it's not clear that their enumerative definition by itself is actually not a problem, but they are integers. And moreover, there's only a finite number of them. I think it's here. There's a finite number. If you fix the curve class, there's a finite number of genus such that they are populated, and above that number, they are just zero. Now this is sometimes called the multi-cover formula. At genus zero is just a very famous formula already found in these earlier papers, which is that even though those numbers are rational, if beta is not a primitive class, then you can rewrite them in this way. Right?
Gromov-Witten invariants are not integers?
No, that's the point I'm making. They are not integers. The Gopakumar-Vafa invariants.
So I missed something on the previous slide. You said there are a number of curves.
Well, yeah, okay. So but I said two things. I say they count these maps, but they count the moduli space of such maps. That moduli space of singularities. They really count the order, well, some kind of intersections on that moduli space. And because of orbifold singularities, they end up being rational. But they are integer in disguise in the sense that if you take them through this map, the numbers that you get here are integer.
I'm sorry, I missed what you say by counting. It's not an integer. Could you
yeah, when I say the word counting, what I really mean is compute the order number of some moduli space of objects. Here would be maps from the Riemann surface to the target. And if that moduli space is singularities, the order number will be rational. It's a criticism you can make actually to the whole story, which is we're trying to count states. What we actually compute is an index, like an order class. And so the index could have constellations between bosons and fermions, and we only have control on these indices.
The index at least is an integer.
Yeah. Well, yeah. Yeah. So the claim is that the correct counting for physics purposes is in fact so the correct counting, if you want to count this bound states of D2 and D0 branes, so the D2 brane is this class beta, then they are given by this Gopakumar-Vafa invariants at genus zero. And the higher genus guys, they actually compute something which is part of the angular momentum of these states. And it's actually also rather important that the counting in that case depends only on this curve class beta, does not depend on the D0 brane charge. Okay, I hope I'm not going into too much technicalities, but it's a bit hard to avoid them. So, yeah, so this is counting these D2, D0 grains on the Calabi-Yau. They are wrapped on some curve. And well, there is actually a very interesting prediction for the growth of such objects coming from thinking of these 4-dimensional black holes as coming from 5 dimensions. So you might know that string theory is in disguise an 11-dimensional theory called M theory, wrapped on some hidden circle. And so these 4-dimensional black holes, they actually lift up to 5-dimensional black holes with some angular momentum. And the correct counting in that case turns out to be some inner combinations of these GV invariants in 5 dimensions. And so the prediction is that they should grow like the entropy of 5-dimensional black hole as a function of the electric charge beta, and M here is the angular momentum. So that's a very sharp prediction from physics. However, currently, because there are it's very hard to control the asymptotic growth of these numbers. What you can do is do numerics and check agreement. And in fact, this numerics was done by Klemm, and Vafa 20 years ago or so. And they found a good evidence that there is the correct growth, at least for static black holes. But if you try to probe a little bit better, more, you'll see that there are also some deviations. And in fact, there's some interesting transitions between black holes and black strings. Just to give you a hint that in general, this controlling the growth of this is a complicated problem. And we have, in some cases, we have numerical data, but it's hard to probe unless you have some sharp prediction like those coming from modularity. Okay, so this was now this a couple of slides about this notion of the Raff category of sheaves and the general framework for counting those states. So as I said, the objects in that category are complexes of sheaves. But they are bounded complexes. So there's a finite number of current sheaves with maps going from one to the next. And the physics understanding of them is that you should think of them as bound states of D branes and anti-D branes. So the sheaves which appear at even grade are like the D branes. They contribute positively to the Chern class. Those at odd places are like anti-D branes. They contribute with a minus sign. And so this framework allows you to take into account the production of brane anti-brane, which somehow can take place in this problem. So those are the so-called BPS states, but they don't need to be normalizable. We want to count actual normalizable bound states. And so for this, you need an extra ingredient, which is the notion of stability condition, which was axiomatized by Bridgeland in 2007. And I'm not going to tell you the whole definition of it, but basically it's a pair of two objects. One is very simple, is the so-called centered charge. So it's a linear map from the lattice of charges to, or lattice of Chern vectors to the complex numbers, whose modulus will give you the mass of your BPS state. But the other key ingredient to make mathematical sense of it is this art A. So this is a subcategory of abelian subcategory of C, which satisfies a bunch of axioms. We don't need to go into them. But just to say that it's actually a very complicated mathematical problem to construct stability conditions on any compact Calabi-Yau manifold. It was only maybe like 5 years ago achieved for the quintic by Lee. But each object in isolation is simple, but the axioms that bind the two are very non-trivial. But once you have them, you can define this notion of generalized Donalson-Thomas invariant, which will be this Euler number of the moduli space of semi-stable objects. Semi-stability means that for any object in the heart, so it's defined for objects in the heart, and you ask that for any sub-object in the heart, the argument of the central charge will be less than that of the object. Might sound well, okay. So that's the definition. And so what Bridgeland has shown is that this space of stability conditions is very well behaved if it's not empty. That's the tricky part. But if it's not empty, it's some complex manifold whose dimension is just the dimension of the lattice. Pretty much you have to, locally, you have to specify the total charges for every basis vector of that lattice. And then you can deform them away while preserving the axioms. And at large volume point, so constructing them is a complicated open mathematical problem in general, but as I said, there's a general strategy to do it at least near the large volume point, which is due to Bayer-Macri Toda. Manuel Macri is here in the mathematical department at Orsay. And it assumes some inequality, which I hope to say a few words later, but which is conjectural in general and has been proven in a couple of cases. Okay, so now, so you have this notion of generalized Donalson-Thomas invariant, which depends on both on the charge vector, the Chern vector gamma, and the stability sigma. But it has this Wau-crossing phenomenon, which occurs on the lines exactly where the central charge, the phase of the central charge of the sub-object gets aligned with the object itself. And the jump is on the other hand, very well controlled. First, it was understood mathematically by Kontsevich, Soberman, and Joyce Song, and then the very appealing physical picture was given for this kind of jump. And in a simplest case, where the objects of charge gamma 1 and gamma 2 are stable on both sides of the wall, but the objects of charge gamma 1 plus gamma 2 jumps, the jump is just the product of the indices on either side times a pairing, a skew-symmetric pairing between the charges, which is sometimes called the Dirac pairing, or is the anti-symmetrized order form in algebraic geometry. And the physics is simply that on one side of the wall, you have two black holes of charge gamma 1, gamma 2, and nothing of charge gamma 1 plus gamma 2. It's not a bound state. But across the wall, there is a third state of charge gamma 1 plus gamma 2, which is this two-centered bound state with two constituents. And if you analyze the quantum mechanics of two black holes with which carry both electric and magnetic charge, then you easily see that the number of bound states is this so-called Dirac factor. But in general, they could have much more complicated decays into a set of multi-centered black holes, and you have to deal with this complication for Calabi-Yau, Calabi-Yau, like the quintic. Yeah, I'm not quite sure how well I'm doing with time, so I'll just continue. But there's no clock here. So it's like 20 minutes. Okay. So in particular, this general notion of generalized invariant, in the case of just curve and point classes, does coincide with this Gopakumar-Vafa invariance. So it's this counting of D2, D0. Okay, there's another counting problem, which is also very well defined mathematically, which is when you have one unit of D6 branch charge that involves the theory of stable pairs developed by Pandari-Pandey and Thomas. And I don't want to say much about it. So in that case, the moduli spaces are much better behaved than in any other example, including Gromov-Witten theory. And so you define this PT invariant. So again, this depends on the D2 and D0 branch charge. You can always remove the D4 branch charge by some kind of answering with flatline bundle. And so there is so this is again a particular version of this Donalson-Thomas invariance. And in fact, there is a general expectation that this counting of stable pairs should be entirely determined by the counting of D2, D0 bound of D2, D0 or Gopakumar-Vafa invariance. This was proposed by Molik, Nekrasov, Okunkov, Pandari-Pandey, and then proven in some variety of examples. The physical idea is that somehow again uses this lift from string theory to N theory. Probably should spare you that kind of details, but it's a very explicit formula which is however kind of non-perturbative in the coupling, string coupling. And the right-hand side here involves this platistic exponential, I guess will be familiar to people working in combinatorics. is just a shorthand for writing what would be an infinite product with exponents determined by this Gopakumar-Vafa invariant. So you might know other versions of this formula in terms of infinite product. But that's that. So if you know how to compute the GV, you know how to compute PT and vice versa. And in a way, you can use this formula to define the GV invariance in terms of well-defined or well-behaved modular spaces.
Excuse me.
Yes.
Is there a factor of n in the denominator or missing in the plethistic exponential? That's not.
Yeah, I think you're right. I should ask. Yeah, there's 1 over n here. I'm sorry.
1 over n, right?
Yeah, I'm sorry about this. Okay, and so one nice thing is that the bound, the so-called Casanova bound on the maximal genus translates into an upper bound on this maximal D0 brane charge. Anyway, so the interest in this talk where these predictions of modularity does not apply either for GV nor for PT, but for these objects that count this so-called D4, D2, D0 brane supporting on divisors. So they are sometimes called rank 0 GT invariant, rank 0 because the 6 brane charge set to 0. So how can we use this to compute this?
And sorry, the omega, the stability conditions, like which stability conditions are you computing these omega for? I mean,
yeah, that's a very good question. Actually, I'll come back to that. So the modularity applies for this invariant in a particular chamber. And for the previous statements I made were in the large volume chamber for.
Yeah.
Okay, so again, the basic physics intuition for modularity comes from this 11-dimensional point of view on string theory. That is that these D4 branes that wrap a divisor or 4 cycle actually are in disguise 5 branes wrapped on the same divisor times a circle. The circle is the M-theory circle. So in disguise, this class of black holes are actually black strings in 5 dimensions. And being black strings, they support some word volume superconformal field theory, which you would get by reducing the 5 brane word volume along the divisor. It's a complicated theory, but it has to preserve a certain amount of supersymmetry. And so you can actually compute the central charges of this from the data and predict the growth of this. But first of all, yeah, the important statement is that these indices, counting this D4, D0, are actually Fourier coefficients in the elliptic genus of that SCFT. So they belong to the protected sector. And if this CFT was at a discrete spectrum corresponding to a nice VOA, then after theta series decomposition, you would get some actual vector-valued modular form just by counting right-moving states in the CFT. So that's basically, this was the prediction from Madesner, Strominger, Witten, that this particular generating series, so you fix the divisor, you also fix the D2 brane charge, and you let this D0 brane charge run. That D0 brane charge turns into the momentum on the circle, so it turns into the excitation level on the SCFT. And then there is some shift as having to do with the central charge and so on. But the prediction is that that object should be vector-valued modular form. But at the time, they did not know about wall crossing, and they did not specify what Z was here in particular. And so we need to refine this a little bit. But if the divisor has some nice properties like being very ample and irreducible, which means it cannot be written as a sum of effective divisors coefficients, then there are actually no walls which extend at large volume. So the choice of chamber is irrelevant. And you can compute the central charges, apply the Cardi formula, and get a precise match with the Bekenstein-Hawking entropy. So this was the big success. Well, it was the version of the big success of Strominger and Vafa, now for arbitrary Calabi-Yau threefold, but for this particular choice of devices, which are kind of smooth and very, very well behaved. And of course, once you have this modularity property, you are in very good shape because the space of this generating series has finite dimension. In fact, the dimension is at most the number of polar terms in these expansions, the number of negative powers of Q. So if you can compute these polar coefficients, then you can completely nail down the Jennings series and then try to compare with other computations at higher order. Well, it's not that simple in general, because when this divisor can be written as the sum of pieces, basically the D4 brane can split into bound states of D4 lower charge. And so the result from that sequence of papers with Sergey and Manshot was that there is a very explicit, so what you get are instead vector valued mock modular forms. Actually, I went a bit too fast here because I did not comment on this issue of vector value. I said it, but I did not emphasize it. So here, there are two indices here. One is determining the 4 cycle that's fixed. The other one is this D2 brane charge, but again by tensoring with flat bundles or using spectral flow in the CFT, you can reduce the second index to just a finite set of values, which is in this discriminant group. So you have to think of this mu as being an index for a vector valued model. Okay, so that's a technicality. Maybe I should have suppressed it. But so now, the statement now, and in fact, I'm suppressing it here. So the statement is that this HP is in general not modular, but there is a non-holomorphic completion H hat, which is entirely determined by the Jennings series associated to the constituents in the possible decompositions, this HPI. So those guys are holomorphic, but you need to, in order to repair the anomaly, you need to combine them with certain theta series in order to obtain something which is modular, but non-holomorphic. Equivalently, the tau bar derivative of this object is non-zero, but it involves also the completions of the constituents. Yeah, and that's not just a general expectation, it's a very precise prescription for what these theta series are. Well, in simpler cases like K3 cross T2, as I mentioned earlier, this is actually much simpler because there are only bound states of 2 centers that contribute. So in this sum of decompositions here, there's just 2 terms, HP, and then the sum of HP1, HP2. And in that case, it was already understood by Moutier-Zagier that this completion was already determined then and exactly related to this, exactly observed that it was the same pattern as in Ramanujan's mock theta series. So the derivation that we produced for this claim is actually the outcome of many years of work, initially in a totally different direction, which was trying to understand the important corrections to so-called hypermultiplet moduli spaces. I don't want to really go into any such detail, but somehow the problem of computing instanton corrections to the low energy effective action in dimension 3, after you put this theory on the circle, is related to the counting of BPS black holes in dimension 4. And by enforcing that these instanton corrections were consistent with the SL2Z symmetry from M theory, right? So, or if you put M theory on Calabi-Yau times the circle, you have this T2, which has an SL2Z antenna. So by enforcing these conditions, after many years of work, we were able to distill them into these very precise predictions for the sum for this theta series. Okay, so so there I have a couple of slides indicating how to produce in general indefinite theta series associated to theta series is associated to indefinite lattices. That's the key feature here. The lattice has not positive signature, but has indefinite signature. I'm going to skip that story. But there is a rather simple prescription due to Marie-France Vignera, also in Paris, a very nice paper from 40 years ago now. The physics of it is that So you look at the quantum mechanics of these two centered bound states. They have, well, it's somewhat like the hydrogen atom. There will be some set of bound states which exist only on one side of the wall. So they contribute to the index like a step function. They contribute, in that case, -2 on one side and 0 on the other side. Maybe this picture should be slightly updated. But the point is that on top of the bound state contribution, there is also a continuum from scattering states in this electromagnetic hydrogen atom, which also is discontinuous. But is not just a step function. As a result, it is non-holomorphic in this parameter tau. And the sum of the two is actually smooth across the wall. So you achieved both modularity and smoothness across the wall by taking together the discrete and continuum part of the spectrum. And this was understood in this paper for two-body setup. But with my student Rishi, we actually managed to extend that to arbitrary number of centers. So that's a nice example of interacting supersymmetric quantum mechanics, where you can compute the full Witten index, including also non-compact interactions. Anyway, so let me now, well, maybe that's a good time to pause, because this was basically the general background, and I'm going to apply that to do some actual computations for the quintic and try to demonstrate why, give very good evidence why the modularity is achieved.
But with LPTHE, like the cocycle can still express as an Euclidean integral for them in the vector valued cases, and it's more complicated.
So in fact, that's a good question. You can rewrite. So you go back to this prescription here. Okay, so here it is. Sorry. So this data series here involves some complicated kernel. So it's a sum of a lattice vectors of n copies of the lattice, and the kernel is some kind of generalized error function. But in fact, you can rewrite it as an iterated Eichler integral of an Euclidean lattice. So it's an iterated Eichler integral, and that's how it manages to satisfy these morphic and domain equations. I could also have said that the way to construct this integrand, we kind of found it in a rather contrived way as a complicated sum of the trees, not unlike the trees in the previous talk. But well, from this work with Rishi, you understand that there's a much simpler prescription in principle, but it's not fully worked out. And moreover, the growth, the exponential growth, does not come from the sum of the trees. It really comes from the exponential growth of each of these factors themselves. I should have emphasized at the very beginning of the talk when I say that you could relax this modularity by using this Eichler integral. Actually, the key point is that this does not affect the leading exponential growth of these coefficients. It does affect the subleading power corrections or logarithmic corrections, but some of the leading growth is insensitive to this. Okay. Yes.
Can I ask another question? So, so going back to the very beginning of your talk, Gromov-Witten invariants depend on a D0 and a D2 brane.
Actually, they are independent of the D0, just dependent.
Even independent of D0. But is there a refinement that also include D4 and D6 branes?
Yeah, so this was what I was explaining. This notion of generalized DT invariant is defined for an arbitrary chain character.
But I wanted Gromov-Witten.
No, Gromov-Witten. No, it's so. Okay. So there is this MNOP relation that relates this DT invariance to Gromov-Witten or Gopakumar-Vafa, but only in a very special case of charge 1 D6 brane. And in fact, the interesting question is whether there is a similar relation for higher D6 brane charge. And the answer to that is not known. It will be some kind of higher rank version of the topological string amplitude. And it's a very interesting question, but Yeah. So the right-hand side, the statistic exponential, which we should also have said, is the topological string amplitude in these guys. There should be some higher rank version of it, which remains to be understood. Maybe it does not need to have any kind of worksheet description like Gromov-Witten. Okay. We have 5 minutes. Okay. And I'll have to be really, really quick in showing you the examples, but that's fine. So I give you the general story. So there's a bunch of examples where I still haven't given you the main tool which to compute this D4, D2, D0. What we know so far are the D2, D0 and the D6, D2, D0. And the main tool is this work of Soheyla Feyzbakhsh and Richard Thomas, which is to basically give a wall crossing formula that relates the two. And okay, it's a long story which I cannot cover, but there is a kind of a way to work in a specific, like simpler set of Bridge-Land stability conditions, which are some kind of degenerate. They don't keep track of the D0 grand charge, so they are not bona fide Bridge-Land stability conditions, but there's a well notion of wall crossing in this family. And most importantly, thanks to the work of Bayer, Macri, and Toda, there is an empty chamber in that slice. So here, you can think of that slice. This is the upper half plane parameterized by the complexified Keller models in this kind of degenerate slice. And Bayer, Macri, Toda have given a conjectural inequality for the existence of stable objects in that slice. So it was a key ingredient in constructing a full Bridge-Land stability condition. And so they claim is that if you choose the Chern classes to be small enough, let's say, there would exist a small region inside this upper half plane under this dotted line where the index is 0. And on the other hand, the index counting this D4 into D0 is at infinite volume. So if you can keep track of all the walls in between, then you are in business. That's would not have been possible without the help of Soheyla Feyzbakhsh, but so together we actually use this technology, and actually basically this wall crossing here is entirely determined by the D2, D0 counting, which we can compute from using this topological string amplitude methods. So I'm happy to continue for another half hour, but I have to stop. So let me just say that by applying this strategy, we developed a theorem that an explicit formula for this PT invariance in terms of DT invariance. We could compute, so we could do such computations for a variety of one parameter models, which include the quintic, but also a few other ones. Basically, so compute the few first coefficients in this generating series, as I said, and check them against modularity. So here I'm showing the answer for the quintic for 1 unit of D4 grand charge along the basic divisor, which is just the pullback of the hyperplane divisor in P4 onto the restriction rather to the degree 5 constraint. So the only numbers we needed to fix are these polar terms with negative powers of Q. So those are the ones underlined in this formula. So from the knowledge of these 7 numbers, and in fact, it was already done many years ago by Gayoto, Strominger-Yin. They also did a similar computation, even though they do not have any mathematical control. You can guess all the other ones, an infinite series of them, if you assume modularity. But in fact, using these wall crossing arguments, we could independently compute all those numbers and so get like 20 minus 7 checks on modularity for the quintic. Okay, so this is the modular form which happens to match these coefficients. As I said, it was guessed earlier, but now there's a mathematical theorem. And in fact, in some of the other cases, the guess was wrong. So we corrected the guess and gave very strong evidence of modularity at this point. to test mock modularity, we have to go to 2 units of D4 brane charge, like wrapping twice this divisor. And this we could not do for the quintic, but we could do for the degree 8 and degree 10, the lines in red in this table. Basically, this table tells you the number of polar coefficients that you need to compute to fix the whole series. So those are the ones with the lowest number of such coefficients. And okay, we also got the confirmation of this modularity property at depth 1. Okay, so I'm sorry that I'm going very fast here, but I'm happy to. So the kind of wall crossing is very complicated. Actually, you have to, even to compute the first term in this series, you have to take into account, in this case, like seven different walls. So obviously it's computer assisted, you don't do this by hand. But maybe so I will just finish on this slide. So far I've explained how, or tried to explain how to go from this counting of Gromov-Witten invariants or Gopakumar-Vafa invariants, which we can do using these holomorphic anomaly equations. Compute from them these PT invariants, counting D6, D2, D0, and then by wall crossing, arriving at these D4, D2, D0, which are the ones which should have this modular behavior and this exponential growth. But we are limited here because we only know those invariants up to a certain genus. So we can only compute a few numbers. In some cases, we are lucky that we could compute many numbers. So we have very good evidence. Now, if you turn this evidence into a postulate, so you require that these Jennings series are actually modular, you get many more constraints. So you can go back the arrows and fit into many more constraints for this direct integration method. So in this way, you can actually push the maximal available genus a few units up. It's not so impressive as I would like it to be, but so the limitation was 53 just from the knowledge of the standard boundary conditions for the topological string amplitude. But by enforcing the modularity for rank 1 unit of D4, you can push it to 69. And if we did not do that because we could not compute that, but we did this for X8 and X10. So this was limited to 60 and 50, but in principle, we cannot push it to 84 and 70. And it's there are some algorithmic limitations that prevent this to go all the way up, but at least that's the target that you can reach. But of course, it begs the main question: is there any independent definition of this invariance which we could evaluate at arbitrary genus, which would enable us to evaluate them at arbitrary genus? And also, is there any mathematical reason why this Jennings series should be modular? So this is the last slide. So mathematically, one might expect that this comes from some kind of VOA acting on the cohomology of this modularized space of stable objects, similar to counting sheaves on surfaces or AB spaces a la Nakajima. But there are other. So in the case where the Calabi-Yau has some elliptic fibration, some Kefi fibration, one can actually make such segments precise. Otherwise, it's a similar problem. We expect it should hold also in multi-parameter families, like in these fibrations. Similar wall crossing arguments do allow to compute higher rank DT invariants. So we have a prediction for this quote unquote higher rank topological string amplitude. Just not have anything. Well, we have a prediction in principle. We don't have anything to compare it in practice. And yeah, this is, as I said, an outgrowth of a different line of thought, which was to understand these incident corrections to hypermultiplied by spaces. And that story is still at not fully finished because we understand the D-brane corrections, but there are other objects in string theory, these Schwarz 5 instantons, which should contribute and make a complete regular complete metric in this modularized space. It's an open problem. So that's it. Thank you for your attention. Sorry for being on.
Okay, so thank you very much. So as before, I propose to move
further discussions and questions for lunch, which is going to be here now. And but okay, so thanks again. And we come back at 2, right? Okay, thank you so much again.